Hi everyone and welcome back. I'm Miguel Alfonso Mendez, and in this video we'll talk about penalized and constrained RBFs for the velocity regression in image velocimetry using our open source software Spicy. This is the third video of the mini course covering the theoretical background of Spicy. In the first video we introduced the general idea of RBF approximations, and we saw how to use them for regression and PDE integration. And in the second video we talked about penalties and constraints. Now we will see how to use these two things, so this framework for the velocity regression. We will take as an example a 2D problem, and you see the generalization to 3D is quite easy, and you can find it also in the original paper. So now in a 2D setting we usually have a set of points xp in which we have velocity data that has two components, u and v, and usually this points is a collector of two numbers of coordinates x and y. So the set of all points in which the data is available can be arranged into a matrix of dimension np times 2. Now in particle tracking velocimetry, the data, and so these points, will be a set of completely scattered, randomly located points. In particle image velocimetry, I mean cross-correlation based velocimetry, this will be available on a regular grid. Now the beauty of Spicy is that this distinction is absolutely irrelevant. Everything works exactly the same in both cases. Now, because of the linearity with respect to the weights, which we discussed in video 1, the velocity field prediction in these points or in any points can be again arranged as a matrix vector multiplication, as I'm showing here, provided that the basis has already been prepared. So you need to know your collocation points and shape factors, and this is the case at the moment. We will see in the last video how to create this basis, but for the moment this basis is given. Now the main reason why the RBF formalism is so interesting in this case is that we can very easily compute derivatives. So here I'm showing you, for example, what's the derivative of the u component with respect to x and of the v component with respect to y. Basically all we have to do is to replace the basis functions with the derivative of their basis functions, which you can also picture as basis functions themselves. So we can make predictions in the same way as we do for the velocity fields, also for all the derivatives. Besides being very useful in the post-processing stage, this fact can also be used to impose constraints or penalties that involve derivatives. Now remember that we want linear constraint or quadratic penalties. Now all constraints that involve derivatives linearly are linear constraints. So for example, if you are dealing with an incompressible flow, like in the case that we will consider in this course, we know that the velocity field should have zero divergence. That's what the continuity equation tells us. The divergence is a linear operator, and therefore we can also turn it into a matrix multiplication, matrix vector multiplication. Here I write our divergence operator acting on the full set of weights linearly. This, we will say, will act on a set of n nabla points which have coordinates x nabla, and we can use this as a linear constraint as it is, or we can take the norm of this product, so the norm of the residual, and square it, and then we will obtain the quadratic penalty as we've seen in the previous video. Now for the velocity regression, as we will see shortly, we usually like to do both things. Now similarly, we can impose Dirichlet conditions as linear constraints. So imagine that we have nd points with coordinates xd, and we know we have to set that these have to be equal to a specific value. So again we will obtain a Dirichlet operator times our vector, and this has to be equal to cd. We can also impose Neumann conditions quite easily. In this case we will need to compute the derivatives along the normal direction of a certain patch or boundary in the domain. Now, these normal derivatives are computed as the projection of the gradient of the velocity on the normal direction. So Spicy will ask the user to provide these normal directions, as we will see. Okay, so imagine that you have a patch which can be a boundary which is inclined in this way. What Spicy will ask for in all the points where the Neumann conditions are introduced is to have these vectors of the normal direction. Once we have these vectors along the relevant points, which we denote as xn, and we have nn of them, then the normal derivatives can be obtained by, as I said, as a projection, and you can easily show that this can be written as using the Schur product, the entry by entry product of the components of the velocity gradients along the components along the normal directions. We will use Dirichlet conditions, for example, to set a zero velocity at the wall, or if maybe we have some velocity probe somewhere in the domain, we want to impose that our reconstruction agree with that specific point, or we can even have a profile or an approximation of a velocity profile which we want to impose. We might use Neumann conditions, on the other hand, to set symmetry conditions in the flow, or if we have, say, an open boundary on which we know that the flow is fully developed along a certain direction, then we want that there is no gradient along that direction. We will use both conditions in the exercises. But now, for the moment, let's say that we have we can collect all of this together. Let's say we have n nabla divergence-free constraints, n d Dirichlet constraints, and n Neumann constraints, and we denote as x nabla, x d, x n the set of points in which each of these is placed respectively. In line with what we saw in the previous video, Spicy will construct a linear system which will usually take the following form. Remember, we are dealing only with linear constraints and quadratic penalties, and so this will produce a block-like structures which we have discussed in the previous videos. Now, in the blocks A, we will have the usual covariance of the bases. This is something that we can compute quite easily once we have the bases. Then we have two penalties. If you don't remember what penalties are, please have a look at the previous video. One penalty is on the divergence-free condition. We can see that which has been introduced as the norm square of the residual of the divergence, and the other is the Tikhonov regularization, which we always had for numerical stabilities. In the constraints, we have all the linear operators related to the constraints that we have discussed before, so d nabla, d, and n. On the right hand side, we have the usual projection of our target on the basis, and the usual vectors that are on the right hand side of our linear constraints. And the unknown are, of course, the vector of weights and the vector of Lagrange multipliers. Note that we have n lambda or Lagrange multipliers, we have n divergence. This is a sort of scalar constraints if you want, and then you have 2nd and 2nn. Here's the 2 because we are in 2D. If you want to go to 3D, you can see easily how this will change. But now, based on what you have learned from the previous video, at this stage you should ask, why are we using the divergence-free condition both as a penalty and as a constraint? And that would be a very good question, and the answer though is quite simple. A penalty, and here you understand the difference between them, is the penalty acts on all points, whereas the constraints usually act only on a few points, which are the n nabla points. If we take n nabla equal to np, then we are making these constraints valid everywhere, and the penalty will be rather redundant. But the key point is that for every constraint we are adding a Lagrange multiplier, and so we are adding an equation. So a constraint will generally make our system larger and, as you will see in the exercises, generally also more difficult to solve. This is why we usually don't put constraints unless it is strictly necessary, and you will see that usually constraints do help in having velocity fields which are smoother and for which the pressure computation can be more easily carried out. Again, you will see this more of this in the exercises, and I encourage you to come back to this video after you have done the exercises to better understand what we are talking about here. Finally, note that if it wasn't because of the divergence-free penalty or constraint, there would be no point in putting together the regression of all the components. As you might have noticed here, we always have that our operators are block diagonal. Okay, so we could carry out each of these regression independently, and this is also something that we will see in the exercises. But in the moment we introduce constraints that involves both components, then of course we need to put together the whole system. Now this is enough for this tutorial. Now in the next one we will move into the pressure computation. See you in the next video.